So the determinant of a matrix. The determinant of a matrix summarizes a square matrix. We write the determinant as determinant of A, or simply with this line on both sides of A. And the determinant is a specific operation. You take the entries of the matrices, the entries of this matrix, and you do an operation, and out comes a number, right? So the determinant of a matrix is a number that you attach to this matrix. For some of you who might remember your multivariate calculus, for example, the determinant of a matrix came out naturally when you were performing a change of variables for multivariate functions, right? And so just as a recollection of that, the determinant of a square 2 by 2 matrix simply written as the product of this diagonals, the first diagonal multiplied with this subtracted from the multiplication of the product of the other diagonal, right? So AD minus BC. That's the definition of the determinant for a 2 by 2 matrix. For a 3 by 3 matrix and so on, it's a little more complicated, although there is a simple trick that you can use to remember the formula. And the trick that I like to do is to essentially extend this matrix, that is, put a copy of the same matrix side by side with it. So A, B, C, D, E, F, G, H, I, right? So we'll put a copy over here. And then we draw lines. Here's one line, here's another line, and here's another line. And we multiply these lines together, right? So A multiplies E multiplies I, and this is what we wrote over here. B multiplies F multiplies G, which is what we wrote over here. And C multiplies D multiplies H, which is what we wrote here. And we do the same for the opposite, the other diagonals, which we here connect them this way. So we do C, E, G plus B, D, I plus A, F, H. However, we take these values, add them together, and subtract from our first computation. Right? And if we say that if the determinant turns out to be 0, this matrix is singular. Right? So as a homework, I ask you to repeat this computation, plug in the formula for this particular matrix, and compute the determinant. Another concept that is important that sometimes you'll hear us talk about is the rank of a matrix. The rank is the number of linearly independent columns or rows of a given matrix. This is always the same number. If you compute the number of linearly independent rows, it's equal to the number of linearly independent columns. We say that a matrix is a full rank when the rank is n, right? Meaning the size of the same size of the number of rows, for example, of the matrix. So, for example, the rank of a matrix is always equal to the minimum of the smallest dimension of the matrix, essentially. So here are some examples of matrices. So here we have matrix. One quick way to do this is to look at the columns. For example, we have 1, 0, 0, 2, 0, 1, and 0, 1, 1. All of these columns are linearly independent, meaning I cannot write, for example, the third vector as a linear combination of the first two vectors, or I cannot write any vector here as a linear combination of the remaining vectors. So the rank of this matrix is 3. Here, on the other hand, I have vector 1 and vector 2, and you can see that the rank of this guy is not full, right? We don't have the same number of independent columns, because one can be written as the value of essentially take this vector, multiply by 3/2, and you have this other vector here, right? So they're not linearly independent, so the rank of this matrix is 2. And of course, when I have two three-dimensional vectors here, I cannot write or two two columns of three numbers each, I cannot write one as a function of the other unless they are the same vector or a multiple, and so here the rank is 2. Right? MATLAB has a command for this, and you simply type rank. Let's talk about matrix inverse, right? And that's an important concept. So let's take two matrices, and some of you might recognize these two matrices as two rotation matrices. You rotate a vector by this angle by multiplying the matrix times the vector. But let's take these two matrices and multiply one to the other, right? So let's write this multiplication here. We have cosine, let me write this down, cosine of theta, sine of theta, minus sine of theta, cosine of theta. And that's our matrix 1. And we're going to multiply this by this other matrix, which some of you might recognize as transpose of one another, but let's just write it this way: cosine of theta minus sine of theta and sine of theta and cosine of theta. And let's do this computation, right? So we take this row here and multiply by this column here and add the results together, so that will be our first entry. So this is going to be cosine squared of theta plus sine squared of theta. Right, so that's our first result. So we do the same thing to get the second column here. So this is going to be the second number, and I'm running out of space here, so I'm going to just put a comma. So we take cosine cosine of theta times, so this is going to be minus cosine theta times sine of theta, and I'm going to run out of space here, so I'm going to put the addition of sine of theta down below here because I run out of space, but cosine of theta, right? And those of you who recognize your, well, let's finish this and then we can do the recognition. So for the second row of my result matrix, I'll have minus sine of theta cosine of theta plus cosine of theta sine of theta, right? And the second entry will be, once again, minus sine times minus sine is just sine squared theta plus cosine squared of theta. So this is my new matrix. And for those of you who remember some of the basic trigonometric identities, cosine squared plus sine squared of theta is equal to 1, right? So we have this on the diagonals. And this addition here, cosine of theta times sine of theta and sine of theta cosine of theta, although this has a minus, this has a plus, so this is 0, right? So these guys disappear, they become 0. And these guys here become 1. So our result here will be 1, 0, 0, 1. And this is what we call the identity matrix. Right? So we define the matrix inverse as any matrix. So let's say you're given matrix B, for example. Any matrix A that I multiply B by, and I get the matrix, the identity matrix, that's called the inverse of B, or vice versa. Right? So let's take a look at some more general notation that we're going to use. For example, for matrices inverses to exist, they must be squared, and at least for this definition. And this is sort of analogous to division, right? If we had just this letter, capital letter A, is referred to single numbers, I could divide A by A, and I would get 1 on the side, right? So the matrix, the identity matrix, which we write as I, is often seen as the equivalent of the number 1, right? So, and we write this the same way as A to the minus 1, right? That refers to the inverse of A. And if I multiply the matrix A by its inverse either from the left or from the right, remember that these two are not the same thing. Nonetheless, in this case, with the inverse definition, the way we define, we always get the identity. Right, so, and with this, we can start, with this notation, we can start doing some algebra. So for example, if I have a matrix times a matrix equals another matrix, which is another way to write our linear system of equations, for example, right? If I multiply both sides by a to the minus 1, so I have multiplied a to the minus 1 times a here, I multiplied a to the minus 1 times c, I multiply from the left, from both sides, I have to do the same thing to the left side and the right side, then a to the minus 1 times a is the identity times b, and the identity times b is simply b, as you can double check. And so the result of the solution to this linear system can simply be written as a to the minus 1 times c, right? This is the equivalent, again, of diffusion. And again, here's the property of the identity times a, or a times the identity is equal to a, right? So this is something you can quickly double check for yourself. Now there are limitations for this matrix inversion operation as we defined. In this case, the limitation is that the matrix must be squared, the matrix must be non-singular, meaning the determinant of A cannot be 0, has to be different than 0. And the other thing to notice is that, as we'll find out in the next video, that matrix inversion is actually computationally expensive. Right? It's not so expensive to divide a number by another number, but to actually compute the matrix that you multiply itself by and get the identity, that can be sort of a cumbersome computation.